All right, so we've been talking about waves and the relationship of frequency and wavelength to the speed of light. We've been talking about the energy of these waves. And now I'm really going to explain what this has to do with actual chemistry and actual atoms. So I've told you that a photon is a particle of light, and that photon acts as a wave or as a particle depending on the circumstances. The same is true of electrons. So here in front of us we have a very simple hydrogen atom. Here we have the nucleus of the atom, and for a hydrogen, it's just one proton, there are no neutrons. So we have a proton in the center, and then, like I said, this is not actually true, but we can imagine that we have electrons that can orbit around it. A hydrogen atom only has one electron. When that electron lies in the shell closest to the nucleus, that is called the n equals 1. When that electron lies in the energy shell closest to the nucleus, that is called the n equals 1, the ground state. That's where it is the most stable, when that electron lies closest to the nucleus. But the interesting thing is there are other energy shells that exist outside of that ground state, and they are specific energy gaps away from each other. That electron can't lie halfway in between. It can only lie at the n equals 1 shell, and then it can lie in the n equals 2 shell. It can't lie in between. So when this electron moves, it has to move a very, very specific energy gap. And the energy gap between n equals 1 and n equals 2 is not necessarily the same as the energy gap between 2 and 3, so on and so forth. We can go ahead and promote the electron from n equals 1 all the way up to n equals 5 if we want to. We would have to just be able to calculate that energy gap. So how do we actually move that electron from n equals 1 upwards? Well, we have to give that electron some energy. So energy is absorbed. When the electron takes in energy, energy absorbed, and that energy can either be in the form of heat, or we can hit it with a photon of light. We know that photons of light have an energy. We know the equation for that. We know that the energy of a photon is equal to Planck's constant times the frequency of that photon. So photons have energy. We can use a photon of light and hit the electron. The electron can then take in that energy. Now that electron is ready to jump up. It goes from being in the ground state to being in an excited state. The energy absorbed by the electron must be equal to the energy differential of the shell. What that really means is you can't go halfway. In order to go from n equals 1 to n equals 4, you have to absorb energy that is exactly equal to that gap. If you absorb less, you can't get all the way up to 4. If you absorb a little more, you can't go halfway. This is called the quantization of energy. I'm trying to make physical chemistry much more straightforward, but energy is quantized. You can't go in between. You can only go from n equals 1 to n equals 4. The energy gap has to be equal to the amount of energy that you have absorbed. So that's what's going on. The electron absorbs energy. It gets promoted to the exact same energy gap. So now, here's the math part of things. This is the hardest equation that you'll be getting this semester. I will do practice problems on this equation from now until the time the final exam rolls around, because I'm sure you'll be asking me about it. We're going to actually calculate the wavelength of light required for that transition. Remember, so the photon is the light that's coming in. It has to have an energy that's equal to the energy gap between n equals 1 and n equals 4. And here is your equation. Drum roll, please. It's called the Rydberg Equation. So the Rydberg Equation is 1 over the wavelength is equal to the Rydberg constant, which is 1.097 times 10 to the 7th meters to the minus 1. That should tell you something immediately. Wavelength, meters to the minus 1. Make sure your units on wavelength are going to be in meters. Times 1 over n1 squared minus 1 over n2 squared. The whole key to getting the Rydberg equation correct is that this cannot be negative. You cannot have a negative wavelength. And so thusly this part, this term of our Rydberg equation can't be negative. In order to make it that this part of the equation can't be negative, n2 has to be greater than n1. Let me get in and solve the math for you, okay? So the question is, what wavelength of light is required for an electron to transition from n equals 1 to n equals 4? So the nice thing, this is a straightforward one, okay, friends? The Rydberg equation is going to get much more tricky, but this is straightforward because we're calculating a wavelength. So we know that we're going to have to solve for wavelength. So check, check, we've got what our unknown value is. We know what our x is in those terms. That's what we're going to be solving for. We have our Rydberg constant that's given to you, 1.097 times 10 to the 7th meters to the minus 1. We have to figure out where n1 and n2 go. One of them is going to be 1. One of them is going to be 4. And rather than trying to memorize that, the bigger number goes second or whatever, let's just try to figure it out, okay? So I told you again, the key. This cannot be negative. So we're going to have 1 over the wavelength is equal to the Rydberg constant, 1.097 times 10 to the 7th meters to the minus 1 times. Now, we've got two choices. We can have 1 over 1 squared minus 1 over 4 squared. Or we can have 1 over 4 squared minus 1 over 1 squared. Which way is going to give you a positive value? 1 over 1 squared minus 1 over 4 squared. It's going to be 1 minus a 16th. So 1 minus a 16th will always give you a positive value. All right, so now we just have to solve. So let me again walk you through the algebra. This is half the battle. Getting this equation set up, half the battle. Let's go through and actually solve the algebra. 1 over the wavelength equals 1.097 times 10 to the 7th meters to the minus 1. 1 minus 1/16. 1/16 is just a number. I have a lot of students who try to leave this as a fraction, or your calculator gives it to you as a fraction. It's just a number. It's just a decimal. That's what I would do. So 1/16 is 0.0625. 1 over the wavelength is equal to the Rydberg constant. Now this is, again, where students do weird things. 1 minus 0.0625 is 0.9375. Now, 1 over the wavelength, we're just going to multiply those two together. 1.097 times 10 to the 7th times 0.9375. 1.028 times 10 to the 7th meters to the minus 1. Now, we have to get the wavelength out of the denominator. The easy way is to take both sides to the -1 power. If that makes sense to you, awesome. If that makes no sense to you, let's go the long way. Okay, so the quick and easy way is take both sides to the -1. And honestly, that is 1000% what I do on my calculator. But if that makes no sense to you, we have to get that out of the denominator. We can't leave wavelength in the denominator to solve this. So to get it out of the denominator, I'm going to multiply both sides by the wavelength. Wavelength on top cancels with wavelength on the bottom on the right, and you are left with 1 equals 1.028 times 10 to the 7th meters to the minus 1 times the wavelength. Now you're going to divide both sides by 1.028 times 10 to the 7th. So your answer then for the wavelength of light that is required to raise an electron from n equals 1 to n equals 4 is 1 divided by 1.028 times 10 to the 7th. That gives you 9.728 times 10 to the minus 8th meters. I think I might have done something wrong. I'm doing this like with you guys on my calculator. Let me just double check my math. So 1 minus 1/16, 0.9375 times the Rydberg constant. And then to the negative 1, 9.728 times 10 to the minus 8th meters. That is the wavelength of light that is required. So in order to get that electron to go from n equals 1 to n equals 4, we need light that has a wavelength of 9.728 times 10 to the minus 7th meters. That is equal to 97 nanometers. And that still really doesn't sound right. Just one more second here. I'm sorry, friends. 1.097 times 10 to the 7th times 1 minus 1/16. Yeah, no, that's right. I thought it was 92. The reason I'm having issues is because I thought it was 92, but I'm obviously confused. There you have it. 97 nanometers is the wavelength of light required to raise an electron from n equals 1 to n equals 4. Okay, so what happens when the electron relaxes? That's called the emission spectra of a hydrogen atom. So if we have, see, this is why I thought it was 92. It's because this is a typo. There we go. So what happens here is when that electron, we just promoted it. We took that electron that was in n equals 1. We hit it with a photon of light that had the specific amount of energy to raise it from n equals 1 to n equals 4. We excited it. That electron doesn't want to stay excited. Everything in chemistry is trying to get more stable. So it doesn't want to stay all the way up there in n equals 4. It wants to fall back down. When that electron falls back down, now it will emit a photon of light. It has to get rid of that energy. Sometimes I like to say it's like if you get kids all hyped up on sugar, they have to let that energy out somewhere or somehow, and so they destroy your living room by throwing toys everywhere. That energy has to go somewhere in order for the kids to relax back down. It's the same with this electron that's excited in the n equals 4 state. When it falls back down into the n equals 1, that energy has to go somewhere. And that energy goes somewhere by being released as a photon of light. So as it falls down, as it relaxes from n equals 4 to n equals 1, it releases a photon of light that has a wavelength of 97 nanometers. So it took 97 nanometers to get it to go up. When it falls back down, it emits a photon of 97 nanometers. So that energy gap doesn't change. It has to absorb it to be promoted. It has to emit it for it to relax. So now, I want you to try. What I would do if I were you right now is I would pause the video and I would actually try to solve this problem on your own. I'm going to just keep going, but we're going to calculate the wavelength of light that is emitted when an electron falls from n equals 5 to n equals 2. So again, if I were taking this class, I would think I was the luckiest person in the world because you got me, and there's only 14 of you. But I would pause, try to solve this before I work you through it on how I would do it. So you're looking for the wavelength of light emitted when an electron falls from n equals 5 to n equals 2. Here's where I'm going to solve it for you. So we're going to use the Rydberg equation. Again, we are lucky. We're trying to solve for wavelength, and that is what is in the equation. I promise it's going to get harder. These Rydberg questions can get super tricky. So we also know what our Rydberg constant is, 1.097 times 10 to the 7th. We have an n equals 5, and we have an n equals 2. Key. This has to be positive. I know that right now it looks real easy, but it's going to get harder. And so I really want you just to remember that that part of the equation has to be positive. So you've got two choices. You can have 1 over 25 minus 1 over 4, or you can have 1 over 4 minus 1 over 25. Whichever one gives you the positive value is the order in which you put them in there. So 1 over 5 squared minus 1 over 2 squared, or 1 over 2 squared minus 1 over 5 squared. 1/4 minus 1/25 is the only way that you can get a positive value. So 1 over the wavelength equals the Rydberg constant times 1/4, 1 over 2 squared, minus 1/25, 1 over 5 squared. Going through and solving the math, 1 over the wavelength is equal to 1.097 times 10 to the 7th, meters to the minus 1. 1/4 is 0.25 minus 1/25 gives you 0.21. Do that multiplication. 1.097 times 10 to the 7th times 0.21 gives you that 1 over the wavelength is equal to 483,777. Again, you got to get both sides. I'm sorry, you have to get the wavelength out of the denominator. The easy way to do it is to take both sides to the -1 power. If you don't know what that means, multiply both sides by the wavelength. That gets it out of the denominator on the left. So then 1 equals 483,777 times the wavelength. Then divide both sides by that 483,777. So the wavelength of light that is required, or I'm sorry, the wavelength of light that is emitted when that electron falls from 5 to 2 is 1 divided by 483,777. 2.07 times 10 to the minus 6th meters. I'm going to convert that into nanometers because that's how my brain thinks about these things. 2,067 nanometers. Well, that's well into the infrared, I'm pretty sure. I'm not sure. I'm not 100% sure, but that's not in the visible range. And so that's the wavelength of light that is emitted when an electron falls from n equals 5 to n equals 2 in a hydrogen atom. So what did this, oh my God, I totally did this super wrong. It should be 434. What did I do? Just 1 second. I am so sorry, my friends. I went astray. I'm trying to find out where I went. Oh, I see what I did. I totally typoed myself on my calculator. I guess that, like, this is why I have COVID, or this is what COVID does to you, is it makes your brain not function properly. I did this wrong. I made a typo on my calculator. So what I'm going to do is I'm just going to use this highlighter thing here, and I'm just going to X out where I went astray. And it was all of this math down here. This is where I went wrong. I'm going to solve the actual math over here. Let's try this again, my friends. I apologize, but again, it's because I have COVID. 1 over the wavelength is equal to 1.097 times 10 to the 7th times 0.21. Gives you, I don't know what happened, 2.034 times 10 to the 6th. So you can see this number was super wrong. 2.304 times 10 to the 6th meters to the minus 1. 1 over the wavelength is equal to that. Then again, I'm going to do the same process, multiply both sides by the wavelength, and then take 1 divided by that number. That gives us that the wavelength of light is 4.34 times 10 to the minus 7th meters, which is 434 nanometers. That makes significantly more sense to me. So when an electron falls from n equals 5 to n equals 2, it emits a photon of light of 434 nanometers of wavelength. And so what does this give rise to? What does this give rise to? It gives rise to the emission spectrum. Sometimes teachers like to show students this when they are in 4th, 5th, 6th grade. Sometimes you do this in high school as well. You look at a light through a grating and you can see the specific wavelengths of light. Hydrogen atoms have this very particular emission spectrum where you can see that you have particular lines in the UV, the visible sequence, and then in the infrared. At least I was right before that the 2000 would have been in the infrared. So this is called the emission spectrum of hydrogen. Each gas has a particular emission spectrum. This is how you can tell the